Okay, so last time what we did, we defined what we mean by the definite integral of a function on an interval from a to b. So how did we define the definite integral? Well, let's say that you have a function f. It is defined on the interval from a to b, and we divide the interval from a to b into we take a partition of the interval from a to b, and the partition divides the interval into smaller subintervals, right? So the partition points are x0, x1, x2, xi minus 1, xi up to xn, and then from each subinterval we pick a sample point. So w1 is a sample point from the first subinterval, w2 is a sample point from the second subinterval, wi is from the ith subinterval, and wn is from the nth subinterval. Well, once we pick these sample points, we form a sum for each subinterval. So I'm going to have a sum with how many summons? The number of summons would be the same as the number of subintervals. So for each subinterval I get a summand. My first summand is I evaluate f at w1 and multiply that by the length of the first subinterval. That's my first summand. Second summand would be I evaluate f at the second sample point w2, multiply that with the length of the second subinterval, and so on. I do it for all the subintervals. So then I get a sum. We call that Rf of p. This is the Riemann sum of f with respect to p. And in summation notation, it is the summation I going from 1 up to n, f of wi times delta xi. What is delta xi? That's the length of the ith subinterval, right? So delta xi is what? What's the length of the ith subinterval? Xi minus xi minus 1, right? So delta xi is xi minus 1. Is everybody okay? So that's the definition of the Riemann sum. And what's the definite integral of f? Well, the definite integral of f on the interval from a to b is denoted by this symbol, which we read as the integral of f of x from a to b. Okay, and it is defined by the limit of the Riemann sum as the mesh of the partition goes to 0. Limit of the Riemann sum as the mesh of the partition goes to 0. This is not a limit. This is not the kind of limit you've seen before. So let me be more precise. What do I mean by this limit? This is what I mean. Let's say the value of the definite integral is L. So what does it mean to say that L is the limit of the Riemann sum as the mesh of the partition goes to 0? Is my question clear? What does it mean to say the number L, I'm just using a letter, number L is the limit of the Riemann sum? What does it mean to say that? Well, this is what it means. I can make the value of the Riemann sum as close to, I can make the value, so this is Rf of p. Let me make a little bit of change here. So what I have here is a number line, and on the number line I drew the number L right here, okay? That's the number L. What I'm saying is that I can make the value of the Riemann sum, so I can make the value of the Riemann sum as close to L as I desire. I can make the value of the Riemann sum of f with respect to the partition P as close to L as I desire by picking the mesh of the partition small enough. So I need to pick the mesh of the partition very close to 0. Okay? So I can make the value of the Riemann sum as close to L as I desire simply by choosing the mesh of the partition close enough to 0. Okay? So if there is a number like this, that's the definite integral. If there is a number like L, that's the definite integral of the function f. Is that making sense? Is everybody okay with that? And so, remember then I defined something I called the left Riemann sum and the right Riemann sum, Ln and Rn. So what is Ln? Well, remember we picked sample points W1, W2, Wn from the subintervals, right? Ln is the Riemann sum when you pick the sample points to be the left end points of the subintervals. So when you pick the left end points of the subintervals as the sample points, you get the left Riemann sum. And you get the right Riemann sum when you pick the sample points to be the right end points of the subintervals. And in this case, we take the length of these. In this case, we take the subintervals having the same length. So all the subintervals, they have the same length. Am I making sense? So when I look at left Riemann sum and the right Riemann sum, usually I assume that all the subintervals have the same length. Is that okay? So what's the length of each subinterval if I ask you that? If I want all the subintervals to have the same length, what's the length of each subinterval? Well, I have the interval from A to B, right? What's the length of that interval? B minus A. And you need to distribute B minus A into n subintervals equally, right? So the length of each one would be what? B minus A divided by n, right? Okay. So how did I write down the Ln in summation notation? What did I do? Look at the ith subinterval, right? Ith subinterval, what's the left end point? Xi minus 1. So you evaluate f at the left end point, multiply by the length of that subinterval, right? So this summation gives you the Riemann sum where the sample points are the left end points of the subinterval. Similarly, Rn, for the ith subinterval, you evaluate f at the right end point xi, right? Is everybody okay? And then I goes from 1 up to n. Is this clear to you? Let's note that so remember we defined the definite integral from a to b of f of x as the limit of the Riemann sum, right? It's a special kind of limit, but it's some sort of limit of the Riemann sum. If that limit exists, then we say that the integral exists, right? If the limit doesn't exist, the integral doesn't exist, right? Now, if the integral exists, that is, if the limit exists, if the integral exists, then I know that the integral will be equal to the limit of ln or Rn as n goes to infinity. Okay? The limit of ln or Rn as n goes to infinity will be the value of the definite integral. Remember, what is ln or Rn? They are also Riemann sums, but they are special kinds of Riemann sums, where you pick the sample points, specifically the left and right hand points of the subintervals. But sample points could be any points, right? But if you know that the integral exists, then it is enough to compute the limit of the left Riemann sum or the right Riemann sum. Okay, we're going to see an example in a bit. So the definite integral does not exist for all functions. Okay? There are functions for which the definite integral doesn't exist. Okay? And but there are functions for which the definite integral do exist. And what functions are they? Well, one class of function is the continuous functions. If you know that a function is continuous on the interval from a to b, then you know that the definite integral exists. Okay? Is everybody clear with that? The definite integral exists if your integrand is a continuous function. And so that's my theorem here. If f is continuous over the interval from a to b, then the definite integral of f from a to b exists. And a remark is that a terminology that we use is that when the definite integral exists, we say that f is integrable on the interval from a to b. So if I say f is integrable on the interval from 2 to 5, it means that f is it means that the definite integral of f exists from 2 to 5. Okay? It's just a terminology. It's like saying f is differentiable at a point, right? When we say that, we mean that the derivative exists there, right? Now we are saying f is integrable over the interval if the definite integral exists on that interval. Okay, let's look at an example now. I want to compute the integral from 0 to 1 of x squared. I want to compute the definite integral of x squared from 0 to 1. If you have seen integration before, until tomorrow, forget about it, because we are going to compute this integral not with using formulas or anything else right now, just by looking at the Riemann sums. Okay. So I want to compute the integral of x squared from 0 to 1. So how would I do it? First of all, is x squared continuous? On the interval from 0 to 1, is x squared continuous? Yes, it's a polynomial function, right? In fact, it's continuous everywhere. And because it's continuous, what do I know? If it is continuous, then I know that the integral exists, right? So I know already that the integral exists, right? Now, if the integral exists, right? If the integral exists, then I can compute the integral by taking the limit of either the right Riemann sum or the left Riemann sum ln. I can take the limit of one of those and find the definite integral. So that's what we're going to do. Before that, let me do an example of finding L4 and R4. So what is L4? What is L4? L4 means that you divide the interval into 4 subintervals with having the same length. Okay? And what are the sample points? Sample points are the left endpoints of the subintervals. Okay? And that's you compute the Riemann sum. So L4 is the Riemann sum where you have 4 subintervals of equal lengths and the sample points are the left endpoints, right? R4 sample points are the right endpoints. So let's see how we can compute L4. I have the interval from 0 to 1, right? I want to divide it into 4 subintervals of equal length, right? What would be the length of each one then? The total length is 1. I have 4 subintervals of equal lengths, so the length of each one would be a quarter. So what are the partition points? First one is of course 0. The second one would be 1/4. What would be the next one? 2/4 or 1/2. The next one would be 3/4, and the next one would be 1. So these are my partition points. How many subintervals do I have? 4. Now, how do I compute L4 then? How do I compute L4? How do I compute L4? Well, it's a Riemann sum where the sample points are what? What are the sample points? Well, for the first subinterval, I have to evaluate f at where? For the first subinterval, I evaluate f at where? 0. Multiply by the 1/4, which is the length of the subinterval. Second subinterval, I evaluate f at 1/4, right? Multiply by 1/4. For the third one, I evaluate f at half, multiply by 1/4. The last one, I evaluate f at 3/4, multiplied by the length of the interval, which is 1/4. You guys realize that you have to do just that in your homework that's due tomorrow. Okay, you have to do that. Well, once I have written down this, right, the rest is just arithmetic, right? So what is f of 0? Remember, f of x is x squared, right? So f of 0 is 0. What is f of 1/4? What is f of 1/4? 1/16, right? Because it's 1/4 squared, right? What is f of half? 1/2 squared, which is 1/4. What is f of 3/4? What's the square of 3/4? 9/16. So remember, the function is x squared. So that's we're evaluating f. We just plug them in. Use your favorite calculator. You'll see that the value is 0.21875. 0.21875. Is everybody clear? Everybody is okay with that? You see how to compute L4. In your homework problem, you're asked to compute some left and right Riemann sums. Okay? In your homework, there are questions where it asks you to compute Riemann sums by using midpoints. What does that mean? It means that you pick the sample points to be the midpoints of the subintervals. Okay, remember that when you do your homework. What is R4 here? R4, let me go back to my intervals. For the first subinterval, I evaluate f where? Where do I evaluate f? For the first subinterval, I evaluate f at the right endpoint, 1/4, multiply by the length, which is 1/4. For the second one, I evaluate f at where? Half, multiply by 1/4. Third one, evaluate f at 3/4, multiply by 1/4. For the last one, evaluate f at 1, multiply by 1/4. And if I do that, this is what I get. Right? F of 1/4 times 1/4 plus f of half times 1/4 plus f of 3/4 times 1/4 plus f of 1 times 1/4. And then we plug in the values of f and do some arithmetic, and we get 0.46875. Everybody's okay? Which one is bigger, R4 or L4? R4 in this case is bigger. There is a reason, because the function x squared between 0 and 1, it's increasing. So whenever you have an increasing function, the right Riemann sum is always bigger than the left Riemann sum. Okay? Now, geometrically, what do they represent? The left L4 and R4. What do they mean geometrically? Let's see that. Okay, what's the meaning of L4 and R4 geometrically? Are you guys done taking notes on R4? Okay, so let's see what do they mean geometrically. Okay, what the graph. Oops. Okay, so this is the graph of x squared, right? Between 0 and 1, the blue curve that I have, that's the parabola. That's the graph of x squared. Remember, L4 L4, what does that represent in this picture? Well, in L4, how many summons do I have? In L4, I have 4 summons, right? 4 summons. What's the first summon? In L4, what's the first summon? It is f of 0 multiplied by what? 1/4. Geometrically, what is f of 0? Geometrically, what is f of 0? It's the height of the curve at 0, right? And I'm multiplying that by the length of this subinterval. So what am I getting? I am getting the area of the rectangle where the length is 1/4, the height is 0, right? What's the second summon in my L4? What is the second summon? Second summon is f of 1/4, right? f of 1/4 times 1/4, right? f of 1/4 times 1/4, that's the second summon. What is f of 1/4? f of 1/4 is the height of the graph at 1/4. So when you multiply that height with the length of the subinterval, what do you get? You get the area of this red rectangle above the second subinterval, right? So what did I do? Above the second subinterval, I created a rectangle, and the height of the rectangle is the height of the graph at 1/4, right? That's what I did. And the area of that rectangle is exactly the second summon in L4. You guys realize that? What is the third summon? What's the third summon in my L4? In L4, the third summon is f of 1/2 multiplied by 1/4. So what am I doing? I am creating a rectangle where the height is f of half, and then I'm multiplying that by the length of the subinterval, which gives me the area of the red rectangle above the third subinterval, right? And I did the same thing for the last one, right? So what is it? What does L4 represent? What does L4 represent? It's the total area of the red rectangles, right? L4 is the total area of the red rectangles. Now, suppose that I am trying to estimate the area below the graph of x squared. Let's say I'm trying to estimate the area below the graph of x squared above the interval from 0 to 1. What would you say? L4 is an overestimate or an underestimate? Underestimate. Let's look at the R4 now. R4, instead of evaluating the function at 0, now I'm evaluating the function at 1/4, right? So for R4, the first summon is f of 1/4 multiplied by the length of the subinterval, right? So you're multiplying this length with the height of the graph at 1/4. So you're getting the area of the magenta rectangle above the first subinterval. The second summon in R4, the second summon, what are you doing? Well, you are looking at f of half multiplied by the length of the subinterval. So you're getting the area of the magenta rectangle above the second subinterval, and so on. So what's R4? R4 is the total area of the magenta rectangles, and if I were to estimate the area below the graph of x squared above the interval from 0 to 1 by using R4, I am getting an what? Overestimate, right? Everybody realizes that? Now here's my question. Suppose now, instead of dividing the interval from 0 to 1 into 4 subintervals, I divide it into 8 subintervals. If I divide it into 8 subintervals, so I'm going to have 4 more rectangles, right? Would I be getting better estimates? Still L4, L8 would be underestimate. R8 would be overestimate, right? Still they are overestimate, underestimate, but they will be more closer to the area below the graph of x squared, right? Now imagine this, instead of 8, 100, 1,000, 1 million, right? The more you pick, the better estimates you get. In fact, the L4, the Ln, and Rn, seems like they are getting closer and closer to the area below the x squared, right? Am I making sense? And in fact, the limit of Ln and the limit of Rn should be exactly what? The limit of Ln and Rn should be exactly the area below x squared. Is everybody okay? So now, without wasting any more time, let's look at Ln. Why should I look at Ln? Because if I look at Ln in general, if I can come up with a formula for Ln or Rn in general for any n, I can take the limit of n, right? I can let n go to infinity and see what's happening to my value. Am I making sense? So let's look at Rn. Well, this is where it's going to be a little bit tougher. In order to find Rn, what do I have to do? First of all, the interval from 0 to 1, I have to divide it into how many subintervals? N. So what would be the length of each subinterval? The length of each subinterval would be? Well, what's the total length? 1. I have n subintervals, so the length of each one will be 1 over n. Right? So what are the partition points? We did this exercise before. What are the partition points? 0 will be the first one, 1 over n will be the second one, the next one will be 2 over n, 3 over n, and so on, right? You have to understand what's the ith subinterval. So what is the ith subinterval here? The ith subinterval is between, notice that the second subinterval is between 1 and 2, right? This is the second subinterval. So the ith one would be between I over n and I minus 1 over n, right? Okay, so how do I compute Rn? For Rn, I look at the ith subinterval. Should I evaluate f at this guy at the right-hand point or the left-hand point? I evaluate f at the right-hand point for Rn, right? So that's what I did. F evaluated at the right-hand point, and then multiply by the length. The length is the same, 1 over n. Each subinterval has the same length, 1 over n. So once I have the summand for the ith subinterval, all I have to do is write summation I going from 1 up to n, right? Once I know the ith summand, all I have to do is write summation I going from 1 up to n. That's the Riemann sum. That's Rn. Is everybody okay with that? You guys are okay with that? I could have write out the summands, more summands, but it's enough. You look at the ith summand and then write down the summation notation. What is f of I divided by n? What is f of x? F of x is x squared, right? F of x is x squared. So what is f of I over n? It will be the square. It will be the square of I over n, right? So you take the square of I over n and you get the second summation, right? So the second summation that I have is what I obtained after I evaluated f of I over n, right? Again, f of I over n is I squared, I over n squared. Well, what is I over n squared? I squared over n squared, right? And then n squared and n can be combined into n cubed. Is everybody okay? Everybody's okay with that? So that's what I have. That's the sum. That's the sum for Rn, right? I can do more. In this summation, 1 over n cubed, n is fixed. Okay? The sum goes over I. So I does not depend on n, right? So I'm going to factor out 1 over n cubed. So I'm going to factor out. So what did I do from going from here to here? I factored out 1 over n cubed. I factored out 1 over n cubed. So what does it do? What does it do when I factor out 1 over n cubed? Well, I have the sum of I squared, right? All I have is summation I going from 1 to n of I squared. What is that sum? What is that sum? It's 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared, right? Is that right? Did I give you a formula for that? I gave you a formula for that sum before the break, and that formula was that this sum is n plus 1, 2n plus 1 divided by 6. That's the value of the sum of I squared. Okay, once I have that, it's just some algebra. What I'm going to do is I'm going to get rid of this n cubed here. How am I going to get rid of that n cubed? What I'm going to do is from n plus 1, I am going to factor out n. From 2n plus 1, I am also going to factor out n. Is that okay? So if I factor out n, what am I getting? If I factor out n from n plus 1, I get n times 1 plus 1 over n. If I factor out n here, I get n times 2 plus 1 over n. So what is good about it? Well, I can cancel out n cubed and the 3 n's I have here. And if I cancel them out, at the end, what do I get? At the end, I get that Rn is equal to 1 plus 1 over n times 2 plus 1 over n divided by 6. That's the value of Rn. Is everybody okay with that? You guys are okay with that? This is the value of Rn. Any questions so far? Any questions? Okay. How do I evaluate ln? Same thing. For ln, for the ith subinterval, what is the ith summand in ln? In ln, the ith summand is f of I minus 1 over n times 1 over n. Instead of evaluating f at the right hand point, I have to evaluate at the left hand point. So that's what I do here. So I evaluate f at the left hand point, I minus 1 over n times 1 over n. The sum goes from 1 up to n. And then, again, what is f of I minus 1 over n? I minus 1 over n, because f of x is x squared, I have to square I minus 1 over n. Right? Then what? Well, then I get I minus 1 squared divided by n squared times 1 over n. Once again, I get 1 over n cubed, and I'm going to factor out 1 over n cubed outside the summation, because the summation is over I, not over n, so I can factor out 1 over n cubed. If I do that, now I'm getting what? The summation I going from 1 up to n of I minus 1 squared. Let's write out what that is. When I is 1, what do I get? When I is 1, I get 0 squared. When I is 2, I get 1 squared. When I is 3, I get 2 squared. Dot dot dot. When I is n, I get n minus 1 squared, right? I get n minus 1 squared. Well, 0 doesn't matter, right? 0 doesn't matter. So let's rewrite this sum. What is that? What is this sum? Well, that sum, I can write it as I going from 1 up to n minus 1 of I squared, right? It's the same thing. Now I apply my formula that I gave you before the break. And if I apply that formula, what I get is this quantity here. So I get this quantity right here. That's the sum of I squared as I goes from 1 up to n minus 1. Remember, for Rn, we went up to n, right? I going from 1 up to n, but now it goes up to n minus 1. So my formula changes by n minus 1. So I get n minus 1 times n times 2 times n minus 1 plus 1. But divided by 6. And you have to simplify that, do the same trick, factor out n, and cancel out n cubed. If you do that, at the end, what you're getting wait a minute. So this is my ln, okay? This is my ln. I don't know why I wrote that here. This is the Rn, right? This is Rn. So this is ln. This is exactly ln. Okay? So what was Rn? Let me go back. Rn is right here, right? Rn is right here. What's the difference between Rn and ln? Yeah, there is just negative here instead of positive. Now think about now what happens as n gets bigger and bigger. What can I say as n gets bigger and bigger? Look at Rn. As n gets bigger and bigger, what can you say about 1 over n? It gets smaller and smaller. In fact, it goes to 0. Right? Imagine n is a million, right? 1 over n is 0.0 something, right? So this is as n goes to infinity, 1 over n goes to 0. So what's the limit of this expression as n goes to infinity? What's the limit of this expression? Imagine 1 over x instead of n. If you feel better psychologically if you have x, right? Because you're used to using x. So what is the limit of this expression as n goes to infinity? 1/3, right? Because this guy will go to 1. The second factor will approach 2. I have a 6. 1, 2, 6 reduces to 1/3. So Rn, in fact, approaches 1/3. What about ln? Same thing, right? ln also goes to 1/3. So what is happening? What's happening is that Rn is approaching 1/3, ln is approaching 1/3 as n goes to infinity. In fact, remember, Rn is an overestimate of the area below the graph of x squared between 0 and 1. ln is an underestimate of the area below the graph of x squared between 0 and 1. So what's happening is that Rn is always bigger than ln, but Rn and ln, they are both approaching to 1/3. Okay? And so what should be the integral? What should be the integral of x squared from 0 to 1? Well, it's the limit of ln and Rn, and that limit is 1/3. Okay? Do I need to compute both limits to come up with the value of the integral? No, I just did it to show you. They are both the same. Okay? And so that's the value of the integral. And what should be the area then? What should be the area below the graph of x squared between 0 and 1? What should be the area below the graph of x squared? It will be 1/3 exactly. Right? The limit of Rn or ln gives you the area below the graph of x squared between 0 and 1. Is everybody okay with that? Questions? Was that tedious to compute integrals by using this type of limits? Well, in fact, it could get very, very tedious depending on what functions you have. And in many cases, you couldn't even do it. Okay? Even if you know that the integral exists. So we are going to do only one example in your homework. That's it, where you have to do these kinds of things. But beginning from section 4.3, we are going to make use of a relationship between antiderivatives and definite integrals. We're going to make use of their relationship in order to evaluate definite integrals. We are going to see that later. But right now, I want to finish by saying a couple of things here. Generally, suppose that I have a function f, which is a non-negative function between a and b. So then I can look at the region below the graph of f, the region below the graph of f. Because f is non-negative, the graph is above the x-axis, right? So then I can talk about the region below the graph of f above the interval from a to b, right? Region below the graph above the interval from a to b. What's the area of that? Well, the area of that region is always the integral from a to b of f of x dx. Is everybody okay? So if I ask you find the area of this region below this graph, you're going to take the integral, right? Now let's assume that f. So what if f is not non-negative? What if f is not non-negative? Then what does definite integral mean geometrically? Well, let's see. Suppose that I have a function f now, and the function f is not non-negative, it has some negative values. But let's just, this is a continuous function over the interval from a to b. What does the definite integral of f from a to b represent? Well, what it represents is the following. Look at the, so I'm going to define a couple of areas here. The area below the graph of f above the interval from a to c is a1. Between C and C prime, this region, I'm calling the area is A2. So this is A2 is the area above the graph below the interval from C to C prime, and A3 is the area below the graph above the interval from C prime to B. Is everybody clear? Then the integral from a to b of f of x dx is what? It's the net area. What do I mean by net area? Regions below the x-axis will have negative areas, okay? So it is a1 minus a2 plus a3. a1 minus a2 plus a3. Is everybody okay? The definite integral, when you have a function like this, it gives you net area, no matter what function you have. I just picked a specific example here, but for any function, if you want to know geometrically what does the integral represent, well, it's the net area. Is everybody okay with that? We're going to make use of that in some of the examples that we... let me do one example right now. Is everybody clear what I mean by net area? Well, actually, no. I'm not going to do any examples because I have to return your exams.